In Chapter 11, we're going to discuss linear regression. An overview of what we're going to look at in linear regression is linear regression is really an extension of correlational analysis, and it's assumed that there's a linear relationship between x and y, which we did kind of see in our previous Chapter 10 with looking at correlational relationships on our scattergrams or scatter plots. A scattergram is produced in a straight line called a line of best fit is drawn through the data points. And I'll show you a slide indicating the best points on a scattergram. Linear regression gives a measure which shows how much the variable y changes as a result of the 1 unit change in the variable x, which is indicated by B. And we kind of discussed that a little bit already with the correlational relationship. Linear regression leads to a mathematical equation, which is called the regression equation. Allows researchers to predict y scores from the x scores. And the test statistics are for the correlation coefficient times the variance accounted for, and B, the slope of the line. And this is how, looking at that correlation and how much the slope actually is identified, they can make for the how much of a relationship there actually is between the x and the y. In simple linear regression, which is what we're actually going to be talking about in this chapter, we predict scores on one variable from the scores on a second variable. So we're looking at one variable, and we can predict scores for that one variable based on the second variable. The variable we are predicting is called the criterion variable and is referred to as the letter y. The variable we are basing our predictions on is called the predictor variable, and it is referred to as x. And so remember, x is going to be our horizontal, y is going to be our vertical on the scatter plot. When there is only one predictor variable, the prediction method is called simple regression. In simple linear regression, which is the topic of this section, the predictions of y when plotted as a function of x will form a straight line. And this is just an example of the line of best fit in simple linear regression, doing a comparison between child's weight and their age in months. So you can see how we have identified this straight line through the scatter plot and how our cases are bundled right around that straight line. And this graph is illustrating the calculation of a regression line. And if you look at the graph, we are going to try and follow the red line on the graph. And what that red line is actually picking up on is the most extreme score on y. Okay, so if we look all the way up on the most extreme score on y, looking at the y-axis, meaning vertically, we're going to see it's 14. And we're going to subtract that 14 from the lowest score on the y-axis, which if you look on, once again, the vertical axis, which is the y-axis, the lowest score is going to be identified as 8. So we go all the way up to the top where we found 14 follow that 14 all the way over. Okay. We mark it and we drop down and we draw all the way over to the lowest score, which is 8 on the vertical axis, gives us 6. So then what we do is we look at the length of the X red line next, okay, and that's going to be our horizontal red line. We follow it all the way over, and if you look at it from the horizontal standpoint, you find that extreme score, which is, if we look at it on the y-axis, we see it as 14, but if we look at it on the x-axis, we see it at about 32.5. So we take that 6 that we already calculated from the y-axis and we divide it into 32.5, which gives us a number of 0.19, and that is the number that we use in our calculation, which we'll see on the next slide. The regression formula that's used, there's 2 formulas. The general formula is y is obviously the variable, and that's in this case the weight, which is represented on the y-axis, is equal to b, which we calculated in the previous slide. I believe it was 1.9, and that's a value representing the slope of the line. And generally speaking, you can identify that on statistical software such as SPSS, but we calculated it ourselves on that previous slide. Times x, which is the value of the scores on the x-axis, plus a, and a is the constant, minus the point at which the regression line crosses the y-axis, which we identified on that previous slide. So if you want to go back and look at that previous slide and just see how we what we actually did, look at it one more time, how we identified the y and the x scores, and how we were able to calculate the slope of the line. And you can also go back in and look at the point where the regression line crosses the y-axis. Okay, so you can see that looking at this slide and then going back and making that comparison to the previous slide. And this is the summary of the past few slides. It's not a long chapter because obviously it's an extension of the correlational analysis that we had just previously looked at in the previous chapter. What it does is it shows the strength of an association between the predictor and the criterion variable. We identified the slope of the line of the best fit, shows how much y changes as a result of the increase in x. It allows us to predict scores from x on a sample where y is unknown. A scatter plot gives us our best line of best fit, and confidence intervals around the line gives us a way of generalizing the population. Inferential statistics show whether the line of best fit is likely to have arisen by sample error or not. And linear regression, or more usually multiple regression, is a correlational technique very much suited to the investigation of natural occurring phenomena.